on reactive synthesis, Rayna. Floor.
Thank you very much, Kuldeep, and yeah, thanks for the organizers for inviting me to give a talk here. Yeah, without further ado, I start with a talk which will be on a topic which kind of has not been mentioned so far in the workshop, namely on reactive synthesis, but I will connect, of course, to satisfiability throughout the talk, and hence the second somewhat kind of pretentious part, which is of the title, which is empowered by logical reasoning. So since this is a session on verified computation, I will start by briefly talking about verification before I go into synthesis. So I'll start with a brief overview of SAT-based verification, which will be very quick, just to emphasize the success that SAT solvers have had in the field of verification. And then I will give a brief overview of synthesis of reactive systems. And finally, I will dive into the main part of the talk, which is where I will discuss how satisfiability and techniques beyond satisfiability are useful in the context of reactive synthesis. All right, so I assume that most of you are familiar with this first part, so I will go relatively quickly through that. And the goal of model checking and essentially of verification is to formally establish via kind of automated techniques that a system or a model of such a system satisfies a given formal specification. So the model checker can either establish that the system is correct and possibly provide some form of proof of that or certificate, or establish that the system is incorrect and provide a counterexample, which is typically an execution of a system that violates the specification. Now, since we are here at a workshop on satisfiability, I will focus on SAT-based model checking, where we start by translating the model and the specification to propositional formulas, and then this allows reducing the model checking problem to a SAT problem. More concretely, we have a finite set of, so here I'm talking about finite state systems, which are where the states of the system are represented via a finite set of Boolean variables. So we have a finite set of Boolean variables, and the states are assignments to those variables. And then we manipulate formulas over the variables, which represent sets of states, and formulas over the variables v and the v prime, the primed version of those, which represent sets of transitions. So by common convention, the primed variables here are the variables at the next state of a transition. So then we have a model which is represented typically as a symbolic transition system, where we have our set of variables v representing the states of the system. We have a formula I over the variables v, which represents the sets of initial states, and a formula t over v and v prime, which represents the transition relation of our symbolically represented transition system. Now, the specifications that we are typically interested in here are temporal logic formulas over these variables v. And an important special case are safety properties, which are defined via some propositional formula over the variables v, which which describes a set of, let's say, bad states or error states, and you want to establish that on every execution, a state that belongs to this set is never visited. So this is very easy to encode into a SAT problem. Namely, we are going to encode the existence of a counterexample, so the reachability of that, by unwinding the model for k steps. So we have k plus 1 copies of the state variables, and then we can say that the zero initially the initial state formula is satisfied. Each pair of successor states satisfies the transition relation, and the state at position k belongs to the set of bad states, namely satisfies the formula bad. So it's clear that this formula is satisfiable if and only if there exists a path of length k that reaches a bad state. So essentially, a satisfying assignment to the variables gives us a counterexample of length k to our desired safety property. And if the formula is unsatisfiable, that means that we don't have a counterexample of length k, so we can increase k and continue searching for larger counterexamples. So this can be this idea can be extended beyond the safety properties to handle all LTL formulas with suitable encoding, and this was kind of the beginning of bounded model checking that started with the seminal paper at TACAS 99 by Beer, Zimati, Clark, and Zhu. So I thought that this can be extended to general temporal logic formulas. Just as another quick example, it can be easily extended to counterexamples to eventually reaching some set of goal states. And the counterexample, which has the form of a lasso path, can be encoded into SAT similarly as before. So we have the unrolling of the transition relation here, starting from the initial states, but only here we have to state that there is a loop somewhere, and that there is a loop to some of the previous states from the stated position k, and that none of these states visits the goal. So this can be extended to full LTL, and furthermore, bounded model checking can be used for verification by choosing large enough k, namely for every finite state model and LTL property phi, there exists the so-called completeness threshold, which allows us to conclude that a model satisfies the formula if we don't find a counterexample of size up to that completeness threshold. And the issue here is that this k is typically very large, and so it's impractical to use in the practical applications, but nevertheless, bounded model checking is a very powerful technique for and can be used for falsification, namely finding counterexamples. Further complete SAT-based techniques have emerged based on the idea and similar ideas as bounded model checking, namely k-induction, abstraction, interpolation, and IC3. I will not go into detailed discussions of these techniques here because I want to move to synthesis at some point. What I want to emphasize is the impact of bounded model checking, namely bounded model checking is widely used since its introduction in the EDA industry, and the work by Beer et al. That introduced bounded model checking has received a range of very solid and prestigious awards, such as the CAF 2018 award, the ETABS 2017 Test of Time award, and the most influential paper of the first 20 years of TACA's award. With that, I gave you a brief overview of SAT-based verification, and convinced you, hopefully, that the SAT-based verification techniques are one of the core engines in formal verification. With that, I will now proceed to the topic of reactive synthesis. So one of the drawbacks of verification is that it's applied only after the system has been implemented. So we need to have an implemented system in order to verify it. The goal of synthesis is more ambitious, namely to construct an implementation automatically from a high-level specification. Now, by construction, the system will be correct with respect to that specification, provided that we have written a specification that actually accurately captures our intention. Even if it turns out that there exists no implementation for the specification, this is still valuable information, especially in the early design phases, because one can establish that the specification is unimplementable and therefore needs to be revised. A synthesis procedure takes a formal specification file that specifies the behavior of the system that we want to synthesize, and either determines that the specification is realizable, which means there exists a system that implements a specification, or determines that the specification is unrealizable, namely there exists no such implementation. Now, in this talk, I will focus on reactive systems, in particular, so finite state reactive systems, which have a continuous interaction with their environment. So those are non-terminating systems, which kind of in a synchronous manner at each step read input from the environment and produce output. And the specifications will be formalized as linear temporal logic formulas, or also omega automata, but here I will just consider linear temporal logic formulas. Now, the reactive synthesis problem has its origins in the 1960s, when it was formulated by Church, with the problem statement that given a specification phi over sequences of evaluations of input and output Boolean variables, we wish to construct a finite state implementation or of a circuit that satisfies the specification for all the possible infinite sequences of input values. Now, as I said, you can think of a reactive system as a system which reads input at each step and produces outputs at the corresponding step. Now, this type of system model has a range of applications, starting from the design of communication protocols, nowadays also in robotic motion planning for synthesizing kind of high-level controllers for robots or other autonomous systems. High level, because here we are again talking about the finite state systems, so essentially finite state control. Now, let me give you a quick example, which is one of the classical examples, and namely an arbiter. So suppose that we want to synthesize an arbiter that serves two client processes. So there we have two input variables, R1 and R2, which model the requests, and we have two output variables, G1 and G2, which model the grants that the arbiter gives to the two clients respectively. Now our specification states that the two grants should never be given simultaneously, and also what we want is that every request Ri is eventually followed by a grant Gi. These two properties, so our specification is the conjunction of these two properties, and they can be formulated, expressed in linear temporal logic as follows. So this box means globally, so something should hold it at every step, and the diamond means eventually, so at some point in the future. So what this formula states is that globally, it's not the case that the two grants are given simultaneously. And also globally, if we have a request R, then at some point in the future, there is an output Gi. One very trivial implementation of such an arbiter is one that completely disregards the requests and then just gives grants to the two processes in a round-robin fashion. So this is a very trivial implementation, and in reality, one would wish to include further constraints in order to prevent such implementation if they're undesirable. Now, since its introduction initially, there has been mostly kind of theoretical developments in the area of reactive synthesis. So Büchi and Landweber showed how via automata transformations the problem can be translated to a two-player game, and Noeli and Rosner later considered the synthesis problem for LTL specifications. So the original problem was essentially formulated for specification in S1S. And they also established that the reactive synthesis problem is hard, namely the LTL synthesis problem is 2x time complete in the size of the specification. So if you think that that NP is difficult, well, this is like we're looking at problems that are 2x time complete. So that's one of the reasons also for which for a long time there was kind of no real kind of developments kind of towards more practical solutions. But in the last 2 decades, there has been many efforts towards actually bringing reactive synthesis closer to practice and to practical applications. So one of the kind of major developments was by Peterman et al. Identifying a fragment which is of LTL, which is expressive enough, but has a better worst case complexity. And this fragment is also kind of the specification form is quite intuitive and then is used in a number of kind of applications in robotic, in a number of robotic applications. Now, in addition to that, there has been very active developments of techniques, starting from kind of abstractions, composition, techniques, and so on, and also resulting from that also synthesis tools. And since 2014, there is an annual SynthComp competition for reactive synthesis tools. Now, in terms of tools, so there are a number of tools that are based on BDDs that manipulate kind of sets of states represented as BDDs, and this is quite natural in the setting because synthesis involves the kind of this inevitable quantifier alternation between the like for the respectively for the input and output. So for every input there exists an output at the corresponding step, and because of the BDD's support for quantifiers, this makes them a natural choice, and a lot of synthesis tools are based on kind of using BDD engines. More recently, there has been also active development of satisfiability-based synthesis methods and tools, and in particular, kind of inspired by the success of SAT-based verification. So one of the prominent approaches is the bounded synthesis approach by Finbarner and Chevy, where one looks at searches for implementations of a given bounded size, and this allows for essentially encoding the problem as a constraint satisfaction problem. And there are a range of other techniques, some of them kind of restricted to safety specifications, for instance, for kind of using QBF and SAT solvers and combined with learning to compute kind of the set of the winning region for a player in a safety game. However, one of the most recent synthesis tools, namely Strix, which implements an explicit method, actually outperforms the symbolic synthesis tools, since its participation in the SynthComp competition starting 2018, since when the tool was developed. So in some sense, in this setting, kind of a tool which doesn't exploit kind of symbolic representation is, at least on the SynthComp benchmarks, more performant than other symbolic techniques for synthesis. However, I will now go on to explain why we are still interested in considering symbolic techniques, and in particular SAT-based techniques, and like why that gives us power to address kind of interesting challenges in synthesis. But first, let me quickly explain the idea of bounded synthesis for LTL specification. So the high-level idea is to, as I said, kind of to look for implementations of bounded size and encode the existence of such an implementation as a SAT problem, or I think in the initial formalization they did that as an SMT problem actually. So the idea is that the formula is translated to universal Kobuch automaton. I will not discuss this part here because there is the time does not allow, and it's not critical for what I want to talk about next. So then the bounded synthesis procedure constructs a constraint system which asserts the existence of such a transition system with a number of states in the system, at most the given bound, and also asserts the existence of a so-called annotation for the automaton and the system, which you can think of it as some kind of witness that certifies that the specification is satisfied. Again, I will not go into the technical details here. Now, in the as I said, kind of in the initial formalization, I think Piner and Sheve considered an SMT encoding with the bounded integers, and they used uninterpreted functions to express the system and the transition relation of the system and its outputs and the annotation. But actually, in follow-up work, they compare different encodings, namely a SAT encoding, where the inputs and the states of the system are represented explicitly, a QBF encoding, which is kind of more symbolic, namely the inputs are symbolic in the sense that so here we have, like in the SAT encoding, there is a conjunction over all the possible inputs at a given step, while here those are quantified, and DQBF encoding, where both the inputs and the states are symbolic. And their results, which you can look up in their paper, show that kind of the QBF encoding was the most had the better performance for the benchmarks that they consider. So I told you that yeah. So although kind of explicit synthesis may perform better, at least on the benchmarks that are part of the SynCom competition, the satisfiability based synthesis, reactive synthesis techniques allow us to make use of techniques beyond the SAT in order to address some of the challenges in the area of reactive synthesis. And I will now go into that, which is on the third part of my talk. So one of the challenges of synthesis, as I see it, as many people say it, is the challenge of writing specifications. So it is critical that the specification that describes the behavior of a system captures all the assumptions on the environment that we had, and also doesn't include the requirements which are inconsistent or cannot be realized together. And this is often difficult if you have requirements that come from different sources, or they describe different features of your system, and you do have to consider them together, although they might turn out to be inconsistent. And also identifying a good set of assumptions on the environment is also quite challenging, because those assumptions should not be overly restrictive for the environment, but on the other hand must still kind of capture any assumptions that are really needed for the specification to be realizable. So what that means is that oftentimes if we write a specification, then the synthesis tool comes back and says that the specification is unrealizable. And as I said, kind of in that setting, one would look at perhaps a counter example, which is a strategy for the environment, and identify how the specification might need to be revised. But in other cases, we might want to synthesize an implementation which in some sense kind of relaxes relaxes the guarantees that the implementation must satisfy, but still in a way that is transparent and that is in some sense meaningful. So let me make this a little bit more concrete. So now we have another arbiter example, which, however, now instead of this response property, which said that the grant should be given eventually, states that the grant should be every request should be granted in the next step. So clearly, this specification is unrealizable because the request can come in simultaneously, and there is no output that can satisfy both of these requirements. However, there exists an arbiter that can grant each request within 2 steps. I mean, we saw an implementation of such a trivial arbiter a few slides back. So in that setting, we would like our synthesis procedure to perhaps produce give us back such an implementation with the clear kind of indication what properties this implementation has, right? So it should not be some arbitrary relaxation of our properties. More concretely, we would like to have to obtain an implementation which is guaranteed to satisfy the specification as well as possible with respect to some precise meaning behind the notion of as well as possible. And I will show you one such case in a couple of slides. Now let me show you another example which illustrates a kind of a different aspect of unrealizability. Now we have an arbiter which I call a patient arbiter. Again, we have our mutual exclusion requirement, but we have the normal response property such that grants should be given eventually for every request. But there is the additional requirement, which gives the name patient to this arbiter, is that a grant should not be revoked while the client keeps requesting it, provided that the client will eventually release the grant, so will drop the request. And this can be specified as follows. So it should be that globally, if the grant is given to client I, and there is the request by client I is raised, but there is the promise that eventually this request will be lowered. Now the grant should still be given in the next step. Again, this specification is unrealizable because the client might never lower the request. And therefore, the request by the other client can never be answered. However, this specification becomes realizable if we assume that each client either releases the grant within some fixed known number of steps or keeps it forever. Let's say our arbiter is a finite state machine, and also if the client are finite state, then we know that if the request was not lowered within certain number of steps, it will never be lowered. So under such assumption, this specification is realizable by a system that waits for the respective number of steps and then then takes away the grant from that client and gives a grant to the other client if needed. So in order to kind of formulate this type of setting in the synthesis problem, we ask for the synthesis of approximate implementations, which are guaranteed to satisfy the specifications for some sequences of input values that belong to a given class. Or we can even relax these further by asking that at least a specified portion of the sequences in that for at least a satisfied specified portion of the sequences in this given class, the specification is satisfied. Note that so here this is some kind of assumption on the environment, but we do not make an assumption in the form of some kind of logical assumption on the behavior of the environment, but it's more of a structural assumption that will capture the cases that the case that we saw on the previous slide with the patient arbiter. So now I will briefly present to you kind of how we can address these two problems, namely the problem of synthesizing an optimal implementation and the problem of synthesizing approximate implementation by leveraging these the encodings of the bounded synthesis problem into kind of satisfiability and beyond formalization. Now, for my quick arbiter, I told you that, that there exists an implementation which satisfies every request within 2 steps, but there are also other implementations, for instance, those that kind of switch by prioritizing requests and grant them in the next step. In particular, I can one possible relaxation of this specification here is one that that says that it's not always that the request is answered in the next step, but this happens infinitely often. So for each of the 2 clients, their request is answered immediately in the next step infinitely often. Otherwise, like for other possibly infinitely many steps, this doesn't have to be the case. So in order to kind of capture this relaxation formally, we consider a problem where we have a hard specification. So these are some parts of the requirements are hard requirements, and the other ones are soft requirements. And this gives kind of this so-called maximum realizability problem, where we are looking for an implementation that satisfies the soft specifications as much as possible. So in order to formulate that precisely, we need to kind of associate a satisfaction value for an implementation and the formula, which has multiple possible values with like depending on how much the specification is satisfied. So our source specifications that we consider are of this nice form. So they're specifications of the form globally something should hold, and this naturally gives us these levels of relaxations, right? When something is satisfied always from some point on, satisfied infinitely often, or kind of stops being satisfied from some point on. And with that, we can define this value function, which captures these cases. Now, like additionally, we need to define how this value, for a conjunction of such sorts of specifications, the values are combined, and that we can do again in a formal manner. Essentially, how this is precisely defined doesn't matter that much for the approach that I will show you. In this case, we prefer that both of these hold infinitely often versus one of them always being true and the other just being ignored. So these are just some examples of this type of value function, but essentially kind of what this formulation gives us is the maximum realizability problem for which we consider the bounded version. So we are looking for a transition system that satisfies the hard specification and is optimal among all the transition systems that are up to that given bound. It's not surprising that we can follow a similar kind of form of encoding as in the bounded synthesis approach, and now arrive weighted instead of a SAT problem, arrive at a partial weighted MaxSAT problem, and this actually has kind of from the generation point of view and from the manipulation point of view, it has a nice structure because only some part of the constraints have to be soft constraints associated with weights, and it's also easy to manipulate them and have different combinations of value functions, as I showed you before. So this gives us a formulation of this maximum realizability problem for bounded implementations as a partial weighted MaxSAT problem. Of course, like the synthesis problem is hard. The size of the instances MaxSAT instances that we have depend on the size of the automata and the number of soft specifications, and they grow pretty quickly with the size of the specification. The instances are part of the MaxSAT competition benchmark set, and we hope to kind of eventually also from the encoding and the synthesis side being able to push this further to more practical application. So I will skip the second part where we have for the synthesis of approximate implementations where the problem is reduced to maximum model counting, but please feel free to look at the reference. I should finish now, right? Yes. So my conclusion is that yes, we know that kind of verification has been one of the major kind of motivations and driving forces behind the development of more performant and better SAT solvers. Actually verification really kind of benefits from this performance. The use of satisfiability solvers in the context of synthesis of reactive systems is still quite far from the same level of maturity and efficiency. So kind of there is at least not inside kind of like this type of kind of industrial applications that can really leverage reactive synthesis and SAT-based techniques for that in the same scale as for verification. Yeah, so like with the example that I showed you, I hope that I convinced you so that that advances in synthesis require effective tools beyond SAT, in particular in the context of synthesis and in the context of synthesis with quantitative guarantees. Optimization plays an important role, such as techniques for MaxSAT or also for maximum model counting, which I didn't have the time to talk about. But yeah, thank you for your attention. And
we have time for one quick question.
Thank you. I'm very intrigued by the use of the box and diamond symbols in the encoding. Are they just for the convenience of talking, or it implies that the underlying logic is Moodle logic?
So the logic is temporal logic. So like the diamond and the box are the temporal operators. Yeah, so
it's not classic logic.
It is a type of
Okay, thank you.
So just the worlds are the sets over time.
Maybe Daniela can set up. Yeah. There any other question?